So let us consider example of water and ammonia molecules. So in the case of water molecule, the central atom is oxygen. So according to valence bond theory proposed by Hitler and London, a bond is formed by overlap of atomic orbitals. So if we consider the electronic configuration of oxygen in its valency shell, it has configuration of 2s2, 2px2, 2py1, 2pz1. So there are two half-filled atomic orbitals, 2py and 2pz. As you can see from the images here, the 2px, 2py, the 2px, the 2py, and the 2pz orbitals, these are mutually perpendicular to each other. So the angle between a 2py and 2pz orbital is 90 degrees. Similarly, in the case of nitrogen, there are 2px, 2py, and 2pz half-filled orbitals, which are at 90 degrees angles to each other. If we assume that pure atomic orbitals were involved in bonding in water and ammonia, then we expect all the bond angles in H2O and ammonia to be exactly equal to 90 degrees. However, this is not the case. The observed bond angle in water is about 104.5 degrees, and in ammonia the bond angle is about 107.5. So clearly there is some problem with this assumption that atomic orbitals, pure atomic orbitals overlap. To understand this, Pauling came up with the idea of hybridization. That is, the s orbitals and p orbitals mix to form sp hybrid orbitals. The hybrid orbitals are more effective in overlapping than pure atomic orbitals. So this is the concept of hybridization. So orbitals which have similar energies, for example 2s, 2p, they can mix to give sp hybrid orbitals. This concept is called hybridization. These hybrid orbitals are better in overlapping than the pure atomic orbitals. So we can have different kinds of hybridization. Sp hybridization, Sp2 hybridization, Sp3 hybridization, Sp3 D hybridization, Sp3 D2, Sp3 B3. So let us discuss these hybridizations one by one, starting with the Sp hybridization. In the case of Sp hybridization, one s orbital and one p orbital combine to give two Sp hybrid orbitals. Here I take example of beryllium chloride to understand the concept of hybridization and bonding. So beryllium valence electronic configuration in its ground state is 2s2. So it has two electrons in the 2s orbital. However, when the electron gets excited, the configuration becomes 2s1, 2px1. One electron gets promoted to the 2px orbital. So now we have two half-filled orbitals, 2s and 2px. These two orbitals combine to form two hybrid orbitals. So here on the right hand side, you can see the two sp hybrid orbitals. So the one pointing towards the right hand side and the other pointing towards the left hand side. So these two hybrid orbitals are at an angle of 180 degrees. So each sp hybrid orbital overlaps with half-filled 3pz orbital on the chlorine atom, forming a BeCl bond. So here we have total two BeCl bonds which are at 180 degrees bond angle. So this is the bonding in beryllium chloride, BeCl. So now let us move to the Sp2 hybridization. Here one s orbital and two p orbitals combine to form 1 plus 2, 3 Sp2 hybrid orbitals. Let us take the example of boron trifluoride to understand this hybridization. Boron in its ground state has a valence electronic configuration of 2s2, 2px1. So it has three valence electrons, but in its excited state, one of the electron gets promoted from 2s orbital to the 2py orbital. So now we have three half-filled atomic orbitals, 2s1, 2px1, 2py1. So these three orbitals hybridize to form three sp2 hybrid orbitals in which are in a planar triangular geometry. Each of these sp2 hybrid orbitals overlap with half-filled 2p orbital on the fluorine atom. So the three sp2 hybrid orbitals overlap with three 2p orbitals on three fluorine atoms, forming boron trifluoride. The bond angle between fluorine, boron, and fluorine is 120 degrees. So this is about the bonding in boron trifluoride. Next, we move to Sp3 hybridization. So here one s orbital and three p orbitals overlap to form four sp3 hybrid orbitals. Let us take the example of methane to understand this. So carbon, the central atom in methane is carbon. Carbon in its ground state has an electronic configuration of 2s2, 2px1, 2py1. However, in its excited state, one of the electron from 2s gets promoted to 2p orbital. So the electronic configuration becomes 2s1, 2px1, 2py1, 2pz1. So now we have four half-filled atomic orbitals which overlap to give four sp3 hybrid orbitals. Each of these hybrid orbitals overlap with half-filled 1s orbital of the hydrogen atom to form a CH bond. So total we have four CH bonds in methane. So the bond angle between hydrogen, carbon, and hydrogen is 109 degrees 28 minutes, and the molecule adopts a tetrahedral geometry. Now let us move to the Sp3 D hybridization. So here one s orbital, three p orbitals, and one d orbital overlap to form five sp3 hybrid orbitals. These five sp3 hybrid orbitals are in a trigonal bipyramidal geometry. So we have a triangular plane and one pyramid going up and one pyramid coming down. So as an example, we consider here phosphorus pentachloride, PCl5. Phosphorus in its ground state has 5 valence electrons, 3s2, 3px1, 3py1, 3pz1. In its excited state, one of the s electron gets promoted to 3d orbital. So we have 5 half-filled orbitals, one 3s, 3p, and one 3d. So these 5 orbitals overlap to form 5 hybrid orbitals in the form of a trigonal bipyramid. So these 5 sp3d hybrid orbitals overlap with half-filled 3pz orbital of the fluorine atom to form PCl bond. So as we have 5 fluorine atoms, we have 5 PCl bonds forming phosphorus pentachloride. So the bond angle between an axial chlorine, that is the chlorine pointing upward, and a equatorial chlorine, that is the chlorine that lies in this triangle, is 90 degrees. Whereas if we measure the bond angle between two fluorine atoms that lie in the triangle, the Cl-PCl bond angle is 120 degrees. Now let us move to Sp3 D2 hybridization. Here one s orbital, 3 p orbitals, and 2 d orbitals combine to form 6 Sp3 D2 hybrid orbitals. So let us take the example of sulfur hexafluoride SF6. Sulfur in its ground state has 6 electrons in its valence shell, 3s2, 3px2, 3py1, 3pz1. In its excited state, 2 electrons gets promoted to 3d orbitals. So we have 3s1, 3px1, 3py1, 3pz1, 3dz square 1, and 3dx square minus y square 1. So these 6 half-filled sp3 D2 hybrid orbitals overlap with 6 half-filled 2pz orbitals on fluorine atom, forming the SF6 structure. So the SF6 is a perfect octahedral geometry with a bond angle of 90 degrees between fluorine, sulfur, and fluorine. So we have like a square and one fluorine going up and one fluorine coming down. So this is a perfect octahedral geometry with a bond angle of 90 degrees. So now let us move to Sp3 B3 hybridization. Here one s orbital, 3p orbitals and 3d orbitals combine to form 7 Sp3 D3 hybrid orbitals. Let us take the example of IF7. Iodine in its ground state has a configuration of 5s2, 5px2, 5py2, 5pz1. So it has 7 electrons in its valenciation. In its excited state, 3 electrons gets promoted to 5d orbital. So we have 7 half-filled atomic orbitals. These 7 orbitals combine to form 7 Sp3 D3 hybrid orbitals in the geometry of a pentagonal bipyramid. So each Sp3 D3 hybrid orbital overlaps with a half-filled 2pz atomic orbital on the fluorine atom, forming IF bonds. So we have total 7 IF bonds located in a pentagonal bipyramidal fashion. And then there are 2 types of bond angles. The bond angle between an axial fluorine atom, the fluorine atom pointing upward, and an equatorial fluorine atom, the fluorine atom that lies in the pentagon, is 90 degrees. Whereas the bond angle between 2 fluorine atoms that lie in the pentagon is 72 degrees. So this is about the concept of hybridization. So we can have Sp, Sp2, Sp3, Sp3D, Sp3 D2 and Sp3 B3 hybridization, in which the orbitals on the central atom combine to form hybrid orbitals, and these hybrid orbitals overlap with atomic orbitals on the other atoms to form chemical bonds. So in this way, Pauling used the concept of hybridization as well as the earlier discussed concept of covalent ionic resonance to discuss bonding in most of the existing molecules at that time. So in the next class, we will discuss molecular orbital theory, which is more widely used theory these days. So thank you one and all.